Good morning! Today is Saturday the 27th of March 2021 and today I'm going to build a climate model. Specifically, I'm taking part in what's called a thinkathon, a physics and astronomy problem solving based hackathon, computer science thing where you spend the day using code to build something. It's starting in about 5 minutes and I've not had my breakfast yet, so I'm going to have to quickly run and do that, and I will explain a little bit more about what this whole thing is in a minute or two. If you're new to the channel, I'm Thomas Rintoul. This is my channel where I do everything science, physics and astronomy mostly, and university related. Make sure you subscribe and hit the bell icon so you don't miss any future videos about what I'm up to.
Hey, Future Thomas here, let me explain. Climate change is real. We are not disputing that in the slightest. Climate change is real, it is caused by humans, and we need to stop emitting carbon emissions. Cool, got that out of the way. Now, climate change is something that is kind of hard to understand scientifically. We can't go and measure everywhere in the atmosphere. We can measure in select places and then use computers to build models to work out what's going on. Now, this idea of building climate models works whether you're talking about anthropogenic climate change, or if you're talking about just the Earth's atmosphere if humans didn't exist, and if you're talking about ice ages. We know there have been a few of these in Earth's history. Some of them have been immortalised in animated movies featuring squirrels that can apparently destroy entire ice glaciers with an acorn. I really want to watch Ice Age now. The thing with climate models is that most of them are owned by big companies or public bodies. Things like the Met Office, they have these global climate models. How hard can it be though? Well, that's kind of the challenge we set ourselves. We decided to tackle a challenge titled Snowball Earth. Our aim was to develop a climate model in about 24 hours to work out how the Earth would get into and back out of an ice age. But I'm going to pass you on to past Thomas to talk about what it's actually like taking part in the Thinkathon, because, well, he's still there.
Okay, so just had the sort of introductory meeting, this is what the hackathon's going to be like sort of thing. So the structure of this weekend is it is currently just before 9:30 and we're about to get started on the project. The structure is that there's going to be a few mini challenges throughout the course of the Thinkathon hackathon thing. These get us extra points. We also get points for things like team spirit, how good our submission actually is for our project. There's a lot of things to get points on, and there are actually prizes, which is exciting. I'm also going to have to take like a little bit of a break from the project at about 11:30 because today is also a visiting day for the university. So we've got offer holders coming to ask us all questions about what it's like being a student at St Andrews in physics. Really should just put them towards this channel.
Okay, Future Thomas is back. The aim is to take the laws of physics that we know about the atmosphere and about the different things that affect the amount of energy coming in and out of the Earth's system, if you could call it, and use that to work out how the Earth could get into and back out of an ice age, and whether or not it could do it multiple times. The aim was to try and get like as many stable climates as possible. To do this, we were given an energy balance model that was created by somebody else, and we had to translate that into Fortran code. There are multiple ways to do this. This is the approach we chose to take because we were sort of hinted towards this energy balance model. There are definitely other ways to do that.
Okay, so it's been an hour and we've made very little progress. We're trying to work out exactly what it is we need to do, and so far we have just a list of things that we think we need to take into account. We don't really know how we're going to do it yet, so we're currently reading a lot of papers and various descriptions of different parts of science. At the minute, I'm drawing rather heavily on a climate model created by Simon Clark, and more accurately the documentation for it created by Tech Wizard. Currently got about an hour till I have to take part in this visiting day thing, so got an hour to make some progress, then got an hour of helping with that, and then probably have lunch, and then hopefully make more progress. Okay, so it's now about lunchtime. I'm going to have some soup for lunch. We've had the visiting day, so I took an hour out for that, but the team's been making progress. We had our first mini challenge, which was to plot an image of either a celebrity or a member of our team. We do each of those individually, so I decided to do Stephen Hawking. Took a JPEG image of Stephen Hawking, converted that in Python to black and white, and then plotted that on a grid, on a Matplotlib plot, and that's been uploaded now as a PNG, so that's 1 point in from my end, and everyone else has done that, so we've got 4 points so far. Now we're trying to work with the climate model. My friend Daniel has worked a bit on getting a sort of basic energy balance model working. There's a bug that we're trying to squash. We're not entirely sure what's causing it, but for some reason one of our constants is suddenly becoming not constant after somewhere in the region of about 40 to 50 iterations. We're not really sure what's going on there, but we've got to work that out. Yeah, we've still got quite a bit of work to do there. We still have a lot of time left. We will get there. We've still got a lot of things to take into account though. Albedo, atmospheric effects. But we've got a lot more work to do. I have my lunch to have, and hopefully by the next update we will have a little bit more progress.
Okay, so the energy balance model. Simply put, an energy balance model is when you've got the same amount of energy coming in as going out. So it's the point where the energy from the sun that's coming in is balanced by the amount of energy leaving the Earth through radiation. There are lots of things that can upset the energy balance model. For example, what we do right now with this anthropogenic climate change. That's climate change caused by humans. We emit loads of greenhouse gases, and that's trapping heat in the Earth's atmosphere. It's reducing the amount of energy that is escaping. At the minute though, that's what we're trying to do. We're trying to set up this energy balance model. We were provided with this energy balance model. It gave us the equations, and there was some code in a language called Perl that we could use to work from. We decided to try and work from that and translate that into Fortran, and well...
Okay, so remember how I said there were like mini challenges for this? Turns out not all of them are coding. This one is very much the get us to get up and do something. So we've been told we have to get an egg as high as possible. It doesn't have to be, we can pick whatever kind of egg we want. Duck, ornamental, chocolate, we're nearly at Easter. So yeah, currently one of my teammates has gone to the shop to buy mini eggs, and he's going to fire it out of an air compressor because he reckons he can get 100 feet in the air or so. I'm thinking I'm going to attach mine to my tripod and stick it out the window, because I reckon I can get that probably up to the tripod on top of the height that the window is at. I reckon I'm like most of the way there, like not 100 feet up, but like I can get it pretty high up off the ground. I've still got to figure out how I'm attaching an egg securely to my tripod. I wonder if I can hold it inside a face mask hanging off a tripod. Yeah, I'm going to see if I can do that.
So while Past Thomas finishes off with trying to get an egg 5.5 foot out of the window, let's go back to the energy balance model and what we're going to try and do once we've got it working. The first is something called albedo. Albedo is a measure of how reflective something is. Something with a higher albedo reflects more of the light that's incident on it, so it doesn't absorb as much, so it doesn't heat up as much. Something like my pasty Scottish skin would have quite a high albedo. Something with a lower albedo would absorb more heat. Something like my t-shirt, which is dark blue, is something with a lower albedo. This is why when you wear a black t-shirt on a hot day, you get a lot hotter than if you wear a white t-shirt. So what we already had built into the model is that when the planet is iced over, when it's actually in an ice age, it has a much higher albedo. This reflects more of the sun's light, it doesn't trap as much. And you might be wondering, well, how are we planning to get back out of an ice age once we get into one? The answer is the greenhouse effect. When the planet is iced over, there is less land to trap CO2. What we are getting CO2 from is volcanism, volcanoes. They emit carbon dioxide when they erupt and do all their other volcano things. Don't ask me, I'm not a geologist. We just found some papers that explain this. Despite it being iced over and reflecting more light, this volcanism is emitting CO2 into the atmosphere, and this builds up over time. This causes a greenhouse effect, like all the CO2 we're emitting, which heats up the planet and causes all this ice to melt. When the ice melts, the albedo decreases again, so we're not reflecting away as much light, and the land and oceans start to trap this CO2 that's been emitted by the volcanoes. This causes the greenhouse effect to decrease, and the planet warms back up again to something similar to this, similar to what we have at the minute, but we're screwing it up. Similar to what we had before the Industrial Revolution. These are all the effects that we want to build into our climate model once we've got this energy balance model bug squashed.
My submission to the egg challenge is this. I have got one duck egg, a University of St Andrews standard issue face mask, some cling film, which I'm going to use to wrap the egg in the face mask to try and stop it falling out. Then I have my tripod, which I'm going to hook the end of the edges of the face mask over this. I then need to get it out of this window as high as I can and take a picture with this camera. Why is this part of a thinkathon? I suppose I was going to say hackathon, but it's because it's a thinkathon, it's physics and astronomy based. And here we have the care package of egg and face mask. So I am going to have to stop filming for this because I need to be able to take a picture and with the camera. So that's us nearly at 5 o'clock. It's been almost 8 hours now that we've been doing this thinkathon. Obviously I took a bit of a break for the visiting day and things like that, but we are now getting towards having some actual progress made. I'm going to be moving on to working on making it iterate in time. My friend Daniel's working on making it more continuous. So instead of going like 5 degrees latitude, 15 degrees latitude up that way, it's going to be more discrete. So trying to do like 1 degree at a time. My friend Jack has been working on how we're going to visualize this with Python, because Fortran's not really good for that. It's more good for churning through things very quickly. It's not great at visualizing, putting things on plots in a way that is actually useful. My friend Laura's been working on sort of the physics for the next stage, the things we're going to have to take into account to make this a more accurate model. Okay, so it's now like 5 to 10 and we've only just managed to get the code to sort of work. We still have to implement all the fancy stuff we want to do with it. And yeah, this is going to be a late night. We knew that going in. This is going to be a long night though. We've still to implement albedo changes. Yeah, there's still quite a lot to do.
So the point we're at the minute is that we have our model printing to a CSV, a comma separated value file. This is essentially just a text file that's got loads of different values with commas between them. That's what we've got it doing. It's printing the values that we need for visualization. So we've got these visualizations and now we're trying to implement some of the extra physics that I've talked about already. And this is where it starts to go wrong. But I'll let Past Thomas explain that.
So we are now at 11:30 and the model still doesn't work. We thought we were making progress and that is clearly not been happening quite as much as we thought it was. We're getting there though, I hope. Currently I'm trying to work out how we can do the correct changes in temperature. I think that our problem currently lies in how we're calculating the change in energy from each surface. Like the amount of energy in versus the amount of energy out. I think there's something wrong. But I can't quite figure out what that is, and that's the problem we're having. Because at the minute, nothing we do seems to change the temperature much at all. The only thing that really changes it is changing the amount of energy coming in from the sun, and that doesn't change on sort of the shorter timescales we're looking at. We're looking at around sort of 50 million years mark. So we need to work out what can change either the amount of energy coming in, blocking some coming in to make it cool down, or what can cause it to hold on to more heat. Okay, it is now 3:10. Now, admittedly, that would really only be 2:10 because clocks went forward, but we started at 9 o'clock this morning. Even if the clocks hadn't gone forward, that is still a really long time to be working on the same thing. And we finally come to the conclusion that we can't do it. Funnily enough, building a climate model in 24 hours is really frickin' hard. I'm exhausted. I can barely keep my eyes open as it is. I can barely hold this camera steady. We've still got a submission to hand in tomorrow, and we are going to do it. It's a bit disheartening to be finishing off this challenge, the coding side of it, like this, but it is what it is. And what it is we went from no knowledge, really, of climate physics beyond me watching Simon Clarke's streams building his climate model, Claude, a global climate model, not what we were doing, so I couldn't just copy it. I'm going to record a bit more about this tomorrow. Once we've got the report, I can explain a bit about what we tried to do, what we wanted to do, why it didn't work. I'm sure you can tell, almost falling asleep standing here, so good night, and I will see you tomorrow morning. Good morning, good afternoon. It is now actually after 12. We have just finished the full Thinkathon, and that means that we are now officially done. We've written the report. It's basically a chronicle of this is what we wanted to do, this is kind of what we couldn't do for various reasons, and yeah, we're finished. And I don't know if you'll be able to hear it in the background, but my shower is currently heating up my bathroom because I am feeling absolutely just drained and I need a shower.
So yeah, it didn't work. We did everything we could to try and make that model work, but fundamentally it wasn't really designed for time iteration. In hindsight, it is very clear to see that we should have gone with my initial idea, which was to work with first principles. Take the basic laws of physics, energy in, energy out, and work from there, rather than using these equations that kind of lumped a load of different atmospheric effects and albedo effects onto about 5 equations. That works great for taking some initial conditions and finding a stable global mean temperature. It's not great for the time iterations we wanted to put in. We had a few problems. We weren't really able to iterate properly. We basically just got to a stable climate after about 3 iterations of time, and then it would just sit there no matter what we tried to do. That being said, we do not want to give up on climate models. Climate models are brilliant. I would really quite like to try this again, but starting from first principles. In fact, if that is something you're interested in, then I have been watching a live stream series from Dr. Simon Clark. He is far more qualified in climate physics than I am, because he has a PhD in it, and he's been building one in Python called Claude. It's named after the capybara mascot of his channel. Basically, the thing we can learn here is if you're going to build a climate model, start from first principles, do it yourself, don't work from an energy balance model you don't entirely understand, and don't try and do it in 26 hours. That was the other mistake we made. That being said, because we did a lot of research and we knew where our problems were, in that we took the wrong approach but our physics was right, we did actually win a prize for this whole endeavour. We won the Best Real World Application Prize for the Thinkathon, which, despite the fact it didn't work, is kind of amazing. Anyway, I really hope you've enjoyed watching this. If you have, then please drop a like, comment down below if this is something you actually found interesting, if you'd like me to talk a bit more about the climate and the physics of climate and make me go and do a whole lot of research on that, which I kind of want to do now, then please put that in the comment section below. Make sure you subscribe and hit the bell icon for future videos. And if you're looking for something that I'm a little bit more qualified to talk about, then maybe check out my video on why there are lakes on Titan? Yeah, that one. I really liked that video. It's a really interesting topic. So go check that out. In the meantime though, I've been Thomas Runtool, and I will see you in my next video. See ya.